Welcome to Unit 9, Redox, Lecture C. Today we're going to be talking about electrochemistry, so half cells, voltaic cells, and electrolytic cells. If you take out your reference tables and open to reference table J, we're going to start by talking about how we can use reference table J to decide what's going to be oxidized and what's going to be reduced. So to review really quick, you know that metals make positive ions. You make positive ions by losing electrons. So what we know from redox oil rig, oxidation is loss. This must be oxidation. Nonmetals tend to make negative ions. You make negative ions by gaining electrons. Therefore, we know that nonmetals are typically reduced. So the really reactive metals are on the top, and the chart already tells you that. These are the ones that are most likely to be oxidized. The really reactive nonmetals are at the top. They're the most likely to be reduced. Now when we talk about oxidizing metals versus reducing metals in an equation, remember that metals can only be positive ions. So for example, lithium from +1 to lithium 0 would be reduction. Lithium 0 to lithium +1 would be your oxidation. So if we look at an equation, like the example listed here, magnesium plus zinc sulfate making magnesium sulfate plus zinc. This is our spectator ion. We can kind of ignore it. What we're really looking at is the interaction between magnesium and zinc. Magnesium, I'm going to change colors, is right here, and zinc is below it. So therefore magnesium is the most likely to be oxidized, and the zinc would be reduced if they're going to react. So the one most likely oxidized is magnesium. The one that's going to be reduced is the zinc. That means that the zinc is going from +2 to zinc 0. The magnesium is going from 0 to +2, and then we can write our half reaction. And this is important because they're not always going to show you the full equation. You're not always going to see the spectator ions. You're not always going to know which one is already 0 and which one is +2. If we had just done the oxidation states, we could have done that without table J. For our half reaction, the one that's being reduced then is zinc. So zinc +2 becoming zinc 0. To go from +2 to 0, you need to gain 2 electrons. Magnesium going from 0 on the left to magnesium +2 on the right. To get that to balance, you need 2 more electrons on the right. The really important thing with table J that they ask quite often, if you look at table J, you'll see that they have hydrogen on here. So here's hydrogen on table J. When we have acids, they all contain H+ ions, and when the H+ gets reduced, it's going to make pure hydrogen gas. So any metal above hydrogen on this table is more likely to be oxidized than the hydrogen is. So if we put any metal on this table that's above hydrogen into an acid, so for example we put magnesium into our acid, we're going to get hydrogen gas and the magnesium is going to get oxidized. It's higher. It's one of the ways, if you know you want hydrogen gas, you can produce it by throwing it into an acid. It's a way to test if something is an acid. You can put one of the reactive metals in it and see if you get hydrogen gas out. Hydrogen's on that table because it's our arbitrary standard. If you remember from lab with redox, we talked about these EO values. Hydrogen gives us an EO value of 0. Everything else is based on whether they are more or less reactive than hydrogen. So when we have a redox happening in one beaker, the oxidation and the reduction happen at the same time. The electrons can easily transfer back and forth to each other. We can use that flow of electrons to create electricity for us to use while it's going from one to the other if we split them apart into 2 beakers. So we split them apart into 2 what we call half cells. Inside of any of your battery, there's actually some kind of semi-permeable membrane that provides us with something we call a salt bridge that makes 2 different half cells. Together they become one full cell. So in your 2 half cells, One of them has oxidation and one of them has reduction in it. We call these batteries voltaic cells. Electrochemistry is going to deal with a chemical reaction that produces a flow of electrons. So in our two half cells, we have a spontaneous reaction. We have it connected with a wire, and this is where our electrons are going to flow. A Salz bridge, and this is where ions are going to flow back and forth. Those spectator ions will move back and forth to keep both sides neutral. We have strips of metal that we call electrodes, and we're going to name the electrodes depending on whether they are in the oxidation half cell or the reduction half cell. And then in your solution, you have the same kind of ions as you have metal. So if I have magnesium for that electrode, I have magnesium ions in my solution. If I have a zinc electrode, I have zinc ions in my solution. So now I have two choices. Either magnesium 0 turns into magnesium and zinc ions turn into pure zinc, or magnesium ions turn into pure magnesium and pure zinc turns into zinc ions. So which one is the one that's going to happen? To figure that out, we use table J. So we find magnesium and we find zinc, and we say magnesium's higher, and we said that on table J, the highest one is the one that is oxidized. So which set has magnesium being oxidized, from 0 to +2 or +2 to 0? Oxidation, the number is going to go up. So this is my correct choice, and this is not going to happen. This is the spontaneous reaction. So I know that the magnesium is being oxidized and the zinc is being reduced. So if I were to write my half reactions out, my oxidation half reaction will be pure magnesium turning into magnesium +2 by losing 2 electrons, and my reduction half reaction is going to be zinc ions gaining 2 electrons to become pure zinc. So my magnesium strip here, my electrode, is going to get smaller because more and more of the pieces are becoming magnesium +2. And my zinc strip is going to become larger because more and more of the zinc are going to be attracted to that electrode and build up into pure zinc. When we name these two electrodes, we have a trick for remembering. We say anox and red cat when shopping for batteries, because this applies to batteries. The anode is where oxidation happens, so we know magnesium is being oxidized, that's the anode. The cathode is where reduction happens, and so we know zinc's being reduced, that's the cathode. Anox, red cat. Electrons always flow from the anode to the cathode, so I like to say they flow from A to C, so they're always going to go from what's being oxidized because they're losing electrons to what's being reduced because they're gaining. Because these are losing electrons, this negative anode, the electrons are coming over here and they're attracting all these positive ions and they're getting used up, so the cathode is positive. Just like cats are positive, the anode is negative, the cathode is positive. Okay, so all of those important things about voltaic cells, which are also batteries, are listed right here in your notes. Make sure you study those. We'll be going over lots of examples in class. Electrolytic cells are for the non-spontaneous reactions. So if I want to reduce sodium ions, so in sodium chloride, sodium is +1 and chlorine is -1, into pure sodium and pure chlorine, remember that needs a subscript 2 to be balanced correctly. It's not going to happen on its own. It's not a spontaneous thing. We can't just make pure sodium. Otherwise, every time you dumped salt and water, we'd get pure sodium. We use something called an electrolytic cell. So this is going to be using a battery, using some outside source of electrons to force a non-spontaneous reaction to happen. In all of our electrolytic cells, we are turning ions into pure elements. One of the other things you're going to notice is that there is only one container. There is no salt bridge. It contains a battery. And what's really important here, always the ions going into elements. So as soon as I look at this cell, our electrodes can be of whatever substance. It's going to be a different metal, usually platinum or graphite, something that is non-reactive, so it's not going to get broken down. I'm going to look at my two ions. I have potassium ions and chlorine ions. They are going to turn into pure elements, so the potassium is going to become potassium 0, and the chlorine -1 is going to become chlorine 0. To go from +1 to 0, you have to gain 1 electron. To go from -1 to 0, you have to lose an electron. 2 chlorine atoms means 2 ions, each lose an electron. Those are my balanced half reactions. Potassium's number is going from +1 to 0. That number is going down, so this is reduction. Chlorine's oxidation number is -1. It's going to 0. That number is going up, so that's oxidation. And those would be my half reactions for this cell. Potassium is going to go to the negative electrode. Now notice when I attach a wire to the negative post of a battery, this whole wire becomes negative. It doesn't switch, it keeps its same charge. So when I hook a wire to the positive post of this battery, this whole strip, when we close that switch, will be positive. Opposites attract, the negative chlorines are going to go over here. So the potassiums are going to the negative electrode and they're being reduced. Anox red cat still applies. So if he's going to this electrode and he's being reduced, this must be our cathode. And the chlorines are going to this electrode and they're being oxidized. So this is now our anode. Notice the names for the electrodes are opposite. Their charges are opposite. And this is because it is not spontaneous. So this is a non-spontaneous reaction. We're forcing electrons in. The charges of our anodes and cathodes are reversed. We use electrolysis, one, to get pure metals from group 1 and group 2 because you can't do it any other way. But the other use industrially is in something called electroplating. So if we want to put a thin layer of a very expensive metal on top of a cheaper metal, making things out of pure silver or pure gold or even pure platinum becomes very expensive. Or we want to coat, we want to galvanize a piece of iron or steel with zinc so that it doesn't rust as quickly. We can use this electroplating technique. So we hook the object we want to be electroplated to the negative electrode because we want to attract the positive metal ions. And in this case they're using silver. We want the positive silver ions to be attracted to the object, and then they're using a spoon. And it's going to gain electrons and turn into pure silver. So we want to reduce our metal onto our object into its pure form. So we hook it to the negative electrode to attract it. The negative electrode then, if we're trying to do reduction, is our cathode. We're always hooking our object to our cathode. The oxidation that's happening in this case then, the metal that we want onto our spoon is going to be what we make our anode out of, so that the pure metal turns into the metal ions that we are using to do the electroplating. And so we're going to hook this to the positive post of our battery, and the anode is going to do oxidation. And again, we'll do more examples of electroplating in class, and that is electrochemistry.